Hello, everyone, and welcome to today's presentation. Today's presentation will be titled Pyrolysis. And basically, we are going to learn about what pyrolysis is, the uses of pyrolysis, and what happens to the feedstock during pyrolysis, and application of pyrolysis in chemical engineering. So, first of all, pyrolysis is a chemical process that involves the thermal decomposition of organic materials in the absence of oxygen. This process can be used to produce a variety of valuable products, including bio-oil, syngas, and charcoal. So pyrolysis has a wide range of applications in the chemical, energy, and waste management industries. So basically, the term pyrolysis has Greek roots and can be roughly translated as fire separating. What I mean by fire separating, generally substances that are subjected to pyrolysis undergo a chemical decomposition reaction and break down into multiple product compounds. So basically, the process of pyrolysis is widely used to break down organic substances, for like example, the charring of wood or the incomplete combustion of wood that results in the formation of charcoal. So all these processes I've mentioned involves the use of pyrolysis. Okay, so now we're talking about the principles of pyrolysis. So the first principle is thermal decomposition. So pyrolysis relies on the application of heat to break down complex organic molecules into simpler compounds. So let's take it to the example of frying your chicken or something. So first, when you pour your oil into the frying pan, the oil is very viscous. It's not moving too much like the way the typical liquid would do. But when you apply heat to the frying pan, the heat breaks the bonds existing between the molecules of the oil, making the oil behave less viscous and, as people will say, it's more liquid. Yeah. So point two, oxygen-free environment. So pyrolysis needs to occur in the absence of oxygen. This prevents combustion and allows for the production of valuable products. Point three, temperature control. So a precise temperature control is very important as it determines the composition and properties of resulting products. And point four, reaction kinetics. The rates and the mechanisms of the various chemical reactions that occur during pyrolysis are very important factors in optimizing the process. Okay, so now we're at the pyrolysis processes and its applications. So we have the slow pyrolysis, we have the fast pyrolysis, and we have its applications. So the slow pyrolysis is a process that involves the gradual heating of biomass at low temperatures, typically less than 500 degrees Celsius. And this method is used to produce high quality charcoal. And we all know that charcoal is being produced by wood. When you burn wood at a certain degree of temperature, we get charcoal. So you have fast pyrolysis. Fast pyrolysis involves the rapid heating of biomass at a high temperature, typically between 400 to 600 degrees Celsius. And as we know that temperature is the measure of the average kinetic energy molecules have in a system. So obviously, hence the name fast, because the temperature is obviously higher than that of the slow process. So this method maximizes the production of bio oil, which can be used as fuel for further refination or for further refine. Application. So pyrolysis has a wide range of applications, including the production of renewable fuels, the conversion of waste into valuable products, and the manufacture of activated carbon and other chemicals. Activated carbon is very important in chemical engineering. Yeah. So we have feedstock preparation for pyrolysis. So we have biomass pre-treatment. So feedstock materials such as agricultural waste, forestry residues, or municipal waste, solid waste may require pre-treatment to improve their suitability for pyrolysis. And the size reduction tool is that the feedstocks are often reduced through techniques like grinding or shredding to increase the surface area and to improve efficiency of the pyrolysis process. So as you increase the surface area, there's more contact per centimeter or per meter or per unit measurement of the length. So that also increases the pyrolysis process. And drying is removing the moisture from the feedstock, and that can also enhance the energy content and the overall performance of the pyrolysis system. And we have blending too as well. So blending is basically combining types of feedstocks and optimizing the process and the quality of the resulting products. So when you blend, you obviously mix and add varieties of your initial feedstock with other materials that can enhance the product and make the product better. Okay, so now we're going to talk about pyrolysis, reactor design, and its operation. So every process plant or every reactor has like specific compartments and what happens in that compartment, like the mass spectrometer, how the mass spectrometer turns the organic compound into the gaseous state. Then after, other things happen to that gaseous compound in another chamber before you can get like the sheets and things you're able to read. So there are different chambers in the spectrometer, and applying that knowledge over here to, we also have like different chambers and different processes in the reactor design for pyrolysis. So we are the reactor types. So pyrolysis reactors can be designed in various configurations, such as the fixed bed, the fluidized bed, or the rotary kiln, each with its own advantages and its application. So the fixed bed, the bed is fixed. The fluidized bed, the bed is in a fluid state, and the rotary kiln, the kiln is rotating. Yes, and all of these systems have its own advantages and its applications. And the second point is the process parameters. So the factors like temperature, the heating rate, the residence time, and the pressure must be carefully controlled to optimize the pyrolysis process and yield product results. And the product separation. The products of pyrolysis, including bio-oil, syngas, and charcoal, need to be effectively separated and collected for further processing or utilization. So your plants must have these kind of filtration or these kind of chambers in order for all of these processes to happen and to get separation of results. Okay, so now we're going to talk about the products of pyrolysis and their utilization. As I mentioned earlier on, we have bio oil, we get syngas, we get biochar, and we get some special chemicals like levoglucosan and acetic acid. So let's start with bio oil. So how can we use bio oil? Bio oil is a liquid fuel that can be used as a replacement for fossil fuels or further refined into various chemicals. Syngas is a gaseous mixture of carbon monoxide and hydrogen that can be used as a fuel for feedstock or chemical synthesis. Biochar, a solid carbon-rich product that can be used as soil amendment or fuel or a precursor for activated carbon. And specialty compounds, specialty chemicals. Pyrolysis can produce a range of specialty chemicals such as phenols, levoglucosan, and acetic acid. Okay, so environmental considerations in pyrolysis. So before scientists discovered that there's a process called pyrolysis, and we found out that we can get these kind of products from pyrolysis, we want to mass produce these products. But before we mass produce these products, we need to find a way to make sure that everything is efficient and does not harm the environment in any way. So we are here to talk about the environmental considerations in pyrolysis. So the first point is emissions control. So we need to have proper emissions control systems, which are essential to mitigate the release of pollutants such as particulates, volatile organic compounds, and greenhouse gases. Greenhouse gases can cause global warming and can also, some of the gases can also distort the ozone layer, causing harmful infrared rays from the sun to affect our skins. That's very important. And also, some of the volatile organic compounds, if they are everywhere and they get in contact with a flame, can cause an explosion, and the particulates can also harm your respiratory system. And we need to have proper waste management. We must have safe disposal or recycling of byproducts such as ash or wastewater to minimize the environmental impact of pyrolysis operations. So we need to find a way to properly dispose the waste so that we don't harm the environment in any bad way, and recycle of byproducts to maybe form like other beautiful products. For instance, a plant. I went to a plant, a palm oil plant, and instead of throwing away the nuts, they were able to turn the nuts into another better product for feed for pigs and chickens to eat. So that's another way of recycling of the byproducts. The last point is sustainability. So pyrolysis can contribute to a more sustainable future by converting waste into valuable resources and reducing the reliance on fossil fuels, as fossil fuels are very harmful and they tend to release greenhouse gases and cause global warming. Future trends and developments in pyrolysis. So now that we know about how the pyrolysis system works, how the reactor design also works, we want to see what happens in the future, or we want to predict future trends and developments in this process. So first of all, we need to optimize the design of the reactor. How can we do that? We can do that by improving the efficiency and scalability of product reactors through innovative engineering solutions and feedstock diversification. We have to explore the use of wider range of feedstocks, including municipal solid waste and plastic waste, to expand the applications of pyrolysis as it's restricted in some degree to a particular class of feedstocks. And we need to have integrated biorefineries. We have to combine pyrolysis with other conversion technologies to create an integrated biorefinery system that maximizes the utilization of biomass. This is very important. And advanced product separation. We need to develop more efficient techniques to separate and purify the various pyrolysis products to increase their commercial value. And by the product separation, we'll be able to get at least 99.999999% of the products. That's very important. Okay, so we're going to talk about the future of pyrolysis. It's very important to talk about the future. So basically, this slide is a summary of the previous slide that I gave. So just in case you're not able to follow very well, this is a much more simpler version of what I said in the last slide. So the first point is renewable energy. Pyrolysis can play a critical role in the transition to a suitable low carbon economy by producing renewable fuels and chemicals. Waste management. The ability of pyrolysis to convert waste into valuable products can help address the growing global challenge of waste management. And three, environmental impact. As pyrolysis technology continues to evolve, its environmental impact or its environmental footprint can be further reduced through improved emissions control and waste management strategies. Okay, so off to the final part of this presentation. The first point is so we're going to talk about the conclusion, a summary of everything that we've spoken about from the beginning of the slide to the ending of the slide. And what we've learned is that pyrolysis can be used as a versatile technology in the sense that pyrolysis has a wide range of applications and the potential to play a significant role in the transition to a more sustainable circular economy. And there are currently ongoing research and developments to help better the process of pyrolysis. So continued research and development in areas like the reactor design, the feedstock diversification we spoke about earlier, and the product separation tool will further enhance the capabilities of pyrolysis technology. And the third one is environmental and economic benefits. The environmental and economic benefits of pyrolysis, such as renewable energy production, waste management, and value-added products creation, can make it an increasingly attractive technology. This brings me to the end of this presentation, and this is Group 3. Thank you very much.